Yesterday we kind of examined some of the, the kind of what was called the tour of the periodic table. Have an idea now on some groups you should know: Group 1, Group 2, Group 17, Group 18. They have names. The middle part called transition metals. The stair-step line separates metals and non-metals. Those are the things that you should know on the periodic table. Most of the periodic table is metals. Then very small fraction is going to be non-metals. Metals conduct electricity. They are malleable, which means you can bend them or shape them. They are ductile, which means you can pull them to make wires. Non-metals are brittle. They don't conduct electricity. If you hit them with a hammer, it would, crumble. You can think of like carbon as a really good example. Lead in your pencil is an example of non-metal. It flakes off as you write. You can break it in half. Okay, that's a good example. Today we look at trends in the periodic table. It fits together very well. We've kind of been talking about that as we go along. We've talked about how there's lots of different properties, but there's also some similarities based on the way that it's arranged. And we're going to get into that today. So we're going to look at three physical properties. The only one that's going to make sense to you is called atomic size, which is how big the atom is. The other two you've never heard of before. And we're going to try and explain them as best we can today. So there are several trends in the periodic table. We're going to just pick three properties to look at for this chapter. The three properties. Come on now. Come on, NASA. Tori, what do you want? Nope. Welcome back. There are lots of trends to examine. A trend is a predictable change in a particular direction on the periodic table. Understanding the trend allows you to make predictions about how the chemical, what the chemical behavior of the element is. So for example, you could say this element is probably bigger than this element. This element doesn't react as compared to this element, this other element. So those trends are going to allow us to kind of answer kind of prediction questions about things in the periodic table. It gets a little complicated, so follow along. The first one is called ionization energy. Ionization energy is the energy required to remove an electron from an atom, or an ion, right, from an atom. So, if you have if it requires a lot of ionization energy to remove an electron, that makes it very difficult. So, high ionization energy means hard to remove an electron. Low ionization energy means easy to remove an electron.
No.
Okay, here we go. This gets a little complicated. Ready? You need to draw some things maybe in the back step. So I'll draw on the board for each of those things. But once you see the first one, the rest will kind of fall in place and make sense for you.
What are you drawing?
I'm going to draw the reasons why. Well, first I'll draw the trend for you. Ionization energy, which is abbreviated as IE. The trend is that it increases as you go this way across the periodic table, and decreases as you go down. Yeah, so we're going to say it increases these ways. Should I write increase on there, or would that make enough sense to you? I'll write increase on here. Increasing this way, and increasing.
So the top right is
The most hardest to pull an electron away from. Yes, has the highest ionization energy, which means it's most difficult, and the lowest would be francium, which means it's the easiest to pull away an electron. Let me explain to you the reasons why this is true. Okay, this is where things get a little tricky. First, when you shove electrons as you go across, ionization energy, all about electrons. If you go across, let's just say the second period there, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. So we're going to go across the, second to top row. When you compare all those configurations, you've got 2s1, 2s2, 2p3, 2p4, 2p5, et cetera, et cetera. So what do you notice about all of them? They all have what number? Okay, they're all being put into the same spot, essentially, the second energy level. If we could approximate the atom as looking, I know this isn't right, but if you would imagine this kind of orbit, you know, that we talked about, one of the models is like the orbit, like the Jetson sort of. And if we call this 1s, and then we call this 2s, all the electrons are going here in the same spot, okay? So 1s, 1s, 2, et cetera, et cetera. Does it make sense so far? That's what happens when you go from left to right. As that happens, you got more electrons here, and as that happens, you're adding more charge in here. Because every time you add an electron, you're also adding a proton, right? So you're taking electrons and putting them essentially in the same spot, and putting protons in the same spot, and you're really increasing the attraction between the two. So as a result, the atom kind of sucks in, okay, because there's a lot of negative out here, a lot of positive in the middle, and so it kind of becomes really, really stable and sucks in. So when you want to pull away this electron, let's say from neon, well, neon's like the most compact possible, and so this is going to be really difficult to take away this one electron because it's really attracted to this middle part. And so when you go across from left to right, the reason that it increases is because you're putting electrons and protons essentially in the same spot. Make sense? Max, it does. Does anyone else make sense?
Yes, it makes sense.
So it sucks in. It's really happy. It's hard to pull those electrons away. Okay. Now, it's easier to say the opposite of this. When you go down a group, every time you go down a group, you're putting electrons in a different energy level. So if we just go down the first group, we got lithium, that's 1s. And then you get a new ring. I know they're not rings, but you get the idea. That's 2s. And then you get a new ring as you go to, what's that, potassium, that's 3s, and so on and so forth, right? And so, not only is there a giant distance between, you know, these electrons.
No, this lithium is 2s.
Oh, what did I say? I meant potassium, for 4s.
Alright.
But, it's okay. We're all good. So every time you go down a column, or down a group, you're putting another ring on the atom. No, it's not a ring, but I'm just going to say it's a ring for purposes of drawing it on the board. But anyway, so the electron's further and further away, right? So it's easier to take away this electron because it's further away from the nucleus than it is this electron, this electron, and this electron. And that's why it decreases as you go down a group. I wrote it opposite. Okay, it decreases when you go down a group, which is easy. So if something that's big, like let's say francium, that electron's way out here. Okay? And it doesn't really feel that attracted to this nucleus. So the energy required to pull away this electron is very, very low because it's very simple to do. Francium's big and fat. It's got like 87 electrons. Okay? And so it doesn't really care if it loses one that much. You can just kind of pluck it away because it's far away. Yeah, exactly. It's very easy to give that electron away because it doesn't really care, you know, if it has. Yeah, and then kablamo.
Well, so why doesn't 114 react more than 87?
Because you're moving to
Well,
the
the
right,
Quadium.
next to you.
Well, yeah, when you go right, then you get this thing, you know, where you have it all in the same spot. They're kind of packed in tight together, and it's hard to pull it away. Francium, you got another level, and it's very easy to pluck that electron away. And not only is distance a factor here, but remember, electrons are attracted to protons, right? They are attracted to each other. I just said that, but twice.
So is radium kind of.
But when you have another effect happening, if there's a bunch of electrons in between this electron, the one I want to take away, and this proton, then that reduces the effect of this attraction. Okay, this is where the positive charge is in here somewhere. So this electron attracted to this part, but if there's like, you know, 10 electrons in between it, that kind of reduces the attraction it has. And so that's another reason that's very easy to take away this electron. So one is distance. Two is the fact that this electron is it's said to be shielded from the nucleus because there's so many electrons in between it. So it's very easy to take it away. So two reasons there. So if we can review, one is that ionization increases this way because the electrons are being put in the same spot, and the atom actually sucks in and kind of like becomes very happy and not going to lose its electrons. And then going down a group, the ionization energy decreases, and so it's very easy to take electrons away, and that's because of distance and also because of electron shielding, which are both explained in the milk atoms. Verbally saying to you. And these two reasons pretty much apply to everything else. So if you got this, when we do the other two properties, you'll see that it falls right in line with these two reasons. So if you get electron shielding and distance here, and then, well, this is distance that's really close, then you'll be okay. Questions or feelings? You don't like it? It's hard to visualize the reasons because obviously we're never going to hold an electron in our hands, and you know, this is a very kind of rudimentary picture of what's really going on. Rudimentary. What's the next property? Let's make sure I said all these things. Yeah, I said that. You have to write this down?
Yeah.
That down, you have the official definition. I'll make it look better.
Wow, that's terrible.
It is.
The writing is still white.
The writing is white.
White needs.
Please.
You guys just write it down. You kidding me?
That's better.
It's okay, I guess.
You gotta write this down.
Mm-hmm.
This one we're supposed to
So as I just said, electron shielding. Hopefully my definition was better, it made more sense to you, because this one's kind of long and rambling, like most of my lectures. The electron shielding is the reduction of the attractive force between a positively charged nucleus and its outermost electrons through the cancellation of some of that positive charge by the negative charges of the other electrons, the inner ones. I've got a really good analogy for this. You ready for it? When you're done writing. It's really good. Blow your minds.
Hey, what did you say yesterday in the, you said alloy rolling on alloys?
Yeah, what was that?
Because chrome's an alloy. What's an alloy?
Rolling on 20 curves.
That's dubbed in.
I don't know what that means, but
Okay.
just wrote it.
Yeah, who'd you get that from?
I wanted to say something else, but I found out that it's got dual meanings and not appropriate.
Say it.
I'm not going to say it.
Think it.
I'll think it.
Don't worry, it's not on video.
I'll say it off camera. Okay, so electron shielding, I kind of drew the picture for you, but let's just use this fantastic example of what I ate for dinner last night. I had a Reuben, right? I made it in my house.
Oh,
Yeah,
Nice.
everyone loves to shut a Reuben down every now and again. Okay,
So good.
I heat up the sauerkraut. Obviously, the corned beef was hot, and I had the what's the sauce? Thousand Island dressing. Right? I wanted to put the Swiss cheese on it so it melts. So I put the Swiss cheese on. This is a really good analogy. Right on top of the hot sauerkraut and the corned beef. Okay, but if this is so dumb. I need to think of the if I had put, let's say, that Thousand Island dressing on top of the hot part of the sandwich, and then put my cheese on there, the cheese would not have melted, right? Or probably would have, but not as well. Okay? Because the cheese is shielded from the heat by the Thousand Island dressing. Woo! Really good, right? Same idea with that, sort of. Not really,
That
but
sounds delicious.
whenever you can relate anything to a Reuben, it's very important.
So every time I eat a Reuben, I'm gonna think of electron shielding.
Bring in the Thousand Island.
Better if you would say.
Okay, the next one, atomic radius. This one should make sense. How big the atom is. Thank you. The exact size is hard to determine because we have these electron clouds and they have kind of these fuzzy boundaries. And so actual size of the atom is, fairly difficult to determine. But for the most part, we have a fairly good idea. Okay, I think I'm going to say all these things to you, so let's just draw the pictures.
So back to page again?
Back page. Okay, atomic size. Atomic size or atomic radius is going to follow the same trend as ionization energy. Atomic size, well, actually it's the opposite trend, my fault. Atomic size is going to decrease this way. How do you want me to write them?
Put the arrow the other way.
Okay, that's what I thought. So it's going to increase this way and increase this way. Increase
Now you got me all screwed up.
and increase.
So bottom left. So for instance would be
Yeah.
the best one.
Yes, this is the best one.
It's an increase. Alright, so the reason that the trend is this way are the exact same reasons as we just listed for ionization energy. So let's take a look. First of all, when you go down a group, the size increases. As Corey said, francium is going to be the biggest atom that we've got. And the reason that it increases is because you add another energy level or another ring. I know they're not rings, but you add another level every time you go down a group. And so you've got 1s, 2s, 3s, 4s, all the way down to 7s. There's lots of rings, okay? So there's that distance thing, and what's the other thing that happens too? What's this? What's actually happening here? Electron shielding. This electron here can kind of roam because it's not really that attracted to the nucleus. And so that also increases the size a little bit. The outermost electron doesn't really feel this giant attraction to the nucleus because it's shielded by these other electrons, so it makes it even bigger. Okay? Which is the same reason it's also easy to take that electron away. This one. Okay, then when you go across, the size will decrease from left to right. Okay, and that reason is back to this one. You're putting electrons in the same spot this time. If you consider again lithium, you got 2s1, 2s2, beryllium, boron, 2p1, carbon, 2p2, et cetera, all the way up to 2p6. And so all the electrons are in the second energy level, or the second ring. And so they all sit here, and you're adding more charge every time you do it. And so if there's more positive charge here and more negative charge there, then they start to suck in a little bit. And so that's why the size will decrease from left to right. So if I ask you to compare, I'm only ever going to ask you to compare things that are in the same row or column. So if I said which one is bigger, carbon or neon, what would you say? Which element is larger? Carbon or neon? Carbon, because it's more left of neon, okay? If I said which one was bigger, oxygen or selenium, you'd say selenium because it's lower than oxygen. But I'm never going to ask you opposite corners, so don't worry about that. I'm not going to say which one is bigger, nitrogen or sulfur, because you would not have any tools to answer that question. Okay, so here is the other trend. And the last trend, questions, concerns, feelings?
I think we're good.
We're going to the wire here.
Going to bed now?
9-9.
We're moving on to me. Shut up, last play.
It's Cougar Day.
Hey, so come to Xbox.
What?
They're going to Xbox now?
No.
Was it Warfare?
Absolutely.
I think like
You bring it in? What?
My Xbox?
Yeah.
I already bought it here.
What's the last?
I don't know.
Okay.
Show it to us. I bet it's here.
It's up on the desk upstairs.
Are you coming over after school? Yeah.
The last one is something you've never heard of.
It's like 3 in the morning, something.
You've never heard of electronegativity. Electronegativity gets into bonding, which we're going to talk about next chapter. But so we kind of talked about it here. Just one property to look at. It's basically about how electrons are shared. When you have an atom that forms a bond, you're sharing electrons, and they're not all shared equally. And that property is electronegativity. It's basically how much of an electron hog the atom is. And so,
Definitely is in here.
electronegativity, the definition is a measure of the ability of an atom in a chemical compound to attract electrons. Or as I said, how much of an electron hog the atom is.
That's a horrible list I do.
I have a got in my mouth, I can't whistle.
Killing yourself.
Ready? Corey, you got it? Yeah, go ahead.
It would be like, where it's like,
Turn the lights on.
lights
That's
on?
not the way to do it. Okay, thanks. Last one, electronegativity. Electronegativity increases this way and increases this way.
That's the same as.
It's the same direction as ionization energy. Okay, so you really only need to memorize two trends. The reasons are a little bit different. Electronegativity gets into how close you are to 8. Okay? And remember, 8 is the magic number in terms of valence electrons. And so electronegativity, when you go from left to right, you're getting closer and closer to 8. So you're not going to want, so fluorine, for example, the most electronegative element on the periodic table, you don't, and this one you don't count the noble gases. Okay, so we're stopping here.
They already have 8.
Because they already have 8, right? So as we get closer and closer to 8 right here, fluorine is going to be the most electronegative. It's not going to, it's going to hold on to its electrons and then grab any other electrons it can. So it's very, very electronegative. Does not give up electrons very easily. It wants them. On the other hand, going to the opposite corner, frame 2 is big and fat. It kind of doesn't really know where its electrons are, doesn't really want any more electrons because it's got a host of electrons, and so very easy, very low electronegativity here. So electronegativity differs from the first two in the sense that it's all about how close, well, sort of how close you are to 8. Let's define it that way. 8, again, is the magic number of the octet.
Doesn't matter up or down.
It does matter up or down a little bit, but the trend is generally, as you go down, it's going to decrease.